Let's deal with the headline immediately because it matters for trusting everything else in this video. Reality is fine. Nothing broke, no law of physics was violated, and nobody actually sent information backward through time in the way science fiction usually means it. But underneath that exaggerated framing sits a real experiment that genuinely does involve running a quantum system backward, listening for an echo, and using that echo to measure something physicists once thought was nearly impossible to observe directly. This is the real story of what Google's Quantum Echoes experiment actually did, why the phrase time reversal in the description isn't clickbait, and why the honest version of this story is stranger and more grounded in real physics than the exaggerated one. Before we get into it, if you're new here, this channel covers science and technology, stories the way the researchers actually building this stuff talk about them without the exaggeration. If that sounds like your kind of channel, the subscribe button is right there, and it genuinely helps this content reach more people who care about getting the details right. Let's start with the actual experiment, because the mechanics here are genuinely fascinating once you understand what's happening. In October 2025, a team at Google Quantum AI published results in the journal Nature, describing an algorithm called Quantum Echoes, run on Willow, the company's latest generation quantum processor, a lattice of 105 superconducting qubits. The goal of the experiment was to measure something called an out-of-time order correlator, OTOC. For short, a quantity physicists use to study how information spreads and scrambles through a complex quantum system over time. Here's the plain language version of what that actually means. Imagine dropping a small disturbance into a complicated, tightly interconnected system. A single qubit gets nudged just slightly. In a genuinely chaotic quantum system, the tiny disturbance doesn't stay localized. It spreads outward, rippling through every other part of the system it's connected to, becoming so thoroughly mixed into the whole that, from the outside, you can no longer point to where the original disturbance came from. Physicists call this process scrambling, and it's closely related to a quantum version of the butterfly effect, the same basic idea behind the classic thought experiment where a butterfly flapping its wings in one place theoretically influences a storm somewhere else entirely. Except here it's happening with actual measurable quantum information inside a real physical system. The problem is that scrambled information is notoriously difficult to measure directly, because by the time it's spread throughout the system, it's no longer sitting in any one identifiable place. Quantum Echoes gets around that problem using a genuinely clever trick, and it's the part of the experiment that earned the time reversal description. The system runs forward in time. The disturbance spreads and scrambles exactly as expected. Then, rather than trying to measure the scrambled mess directly, the researchers precisely reverse the entire evolution of the system, running the underlying physics backward, undoing the exact sequence of interactions that caused the scrambling in the first place. If everything reverses cleanly, the original signal should refocus, producing a detectable echo, in the same way a sound wave can bounce off a wall and return to its source. Introduce a fresh, different disturbance partway through that reversal, though, and the echo comes back measurably degraded, weaker and altered in ways that reveal genuine, detailed information about how the system's internal structure actually behaves. It's worth being precise that this is a real, controlled manipulation of the quantum system's evolution using its own governing physics, not literal time travel, in any sense that would let information move backward through the ordinary passage of time as you or I experience it. Google's team reported that running this specific measurement on Willow was roughly 13,000 times faster than performing the equivalent calculation on Frontier, currently one of the most powerful classical supercomputers in operation anywhere in the world. Crucially, the researchers described this as a verifiable quantum advantage, meaning the result wasn't simply theoretically impressive in a way that's hard to check. It was independently verifiable, and it held up. That distinction matters considerably in the quantum computing field, since earlier claims of quantum supremacy, dating back to Google's own 2018 demonstration, were sometimes criticized specifically for being difficult for outside researchers to independently confirm. The OTOC protocol used here was specifically designed to sidestep that exact criticism, producing a task that stays genuinely hard for classical computers while remaining efficiently checkable once completed. It's worth being honest about why the specific measurement was chosen rather than some other quantum calculation, because the reasoning tells you something real about where this technology might actually go next. In the researchers' own published words, OTOCs carry quantum interference effects that make them highly sensitive to the fine details of how a quantum system actually behaves, and they're specifically difficult for classical computers to simulate, which is exactly what makes them a genuinely promising candidate for demonstrating practical quantum advantage, rather than just an impressive but ultimately pointless benchmark. Here's where the story connects to something considerably bigger than a single hardware. They've become a genuinely important tool in one of the strangest corners of modern physics, the study of how information behaves inside black holes. Theoretical physicists studying black hole information scrambling, the question of what actually happens to information that falls into a black hole and whether it's ever recoverable, have used OTOC-based models as a mathematical framework for describing that exact process. Black holes are, in a specific theoretical sense, believed to be the fastest possible scramblers of information permitted by the laws of physics, and OTOCs are one of the primary tools physicists use to quantify and study that scrambling behavior mathematically. That connection is real, published, peer-reviewed theoretical physics, not a marketing embellishment, though it's worth being clear that Google's actual experiment measured OTOCs inside an ordinary superconducting quantum processor, not anywhere near an actual black hole, and the connection is a shared mathematical framework rather than a literal physical link between the two systems. The practical, nearer-term application is considerably more down to earth and arguably more immediately useful. Out-of-time order correlator techniques have real, established value in a field called nuclear magnetic resonance, or NMR, spectroscopy, a tool widely used across chemistry and material science to study the internal structure of molecules by tracking how nuclear spins behave inside a magnetic field. Researchers have described the ECHO experiment in exactly those terms: polarization starting on a single spin, spreading outward through a molecular network, then a carefully engineered reversal attempting to refocus that spread. If a fresh disturbance is introduced before the refocusing completes, the resulting echo degrades in a specific, measurable way, and how it degrades carries genuine information about the molecule's internal structure. That's a real, concrete application researchers are actively working toward, with potential relevance to studying everything from complex molecules to magnetic materials, and, more speculatively, other systems that exhibit similar quantum scrambling behavior. It's genuinely important to include the honest caveats here, because this is exactly the kind of story that gets flattened into pure hype in a headline, and doing that would be a disservice to how interesting the real, bounded version already is. Researchers covering the experiment have been direct that meaningful, real-world applications built on this specific technique will still take years to develop. This is one genuine, verified step on a considerably longer road toward quantum computers that are broadly practically useful across many different fields, not a finished tool ready for immediate deployment in a chemistry lab or a black hole physics department. The demonstration proves the underlying technique works and that it offers genuine, verifiable computational advantage over classical methods for this specific, narrow task. It doesn't yet prove the technique is ready to solve open scientific problems that current classical tools can't already handle in practice, and Google's own researchers have been careful not to claim otherwise. So here's why any of this should matter to you beyond the exaggerated headline. This experiment represents something genuinely significant in the long, difficult effort to build quantum computers that do more than just prove they're theoretically faster than classical machines at contrived artificial tasks. It's a demonstration of quantum hardware tackling a real scientifically meaningful measurement. One physicists in an entirely separate field, black hole theory, have already found genuinely useful as a mathematical tool, and doing so in a way that other researchers can independently verify rather than simply take on faith. That combination, real scientific relevance plus independent verifiability, is precisely the bar quantum computing has struggled to clear consistently, and clearing it even once on one specific well-chosen task is a legitimately meaningful milestone without needing any embellishment about broken reality or backward time travel to make it worth paying attention to. There's also something worth sitting with about why researchers reach for language like time reversal and echoes in the first place, rather than simply calling this experiment measuring a correlation function, which is technically what's happening, but conveys essentially nothing to anyone outside the field. The metaphor genuinely captures something true about the underlying physics. Information really does spread outward like ripples. The system really is run backward through its own governing equations, and the resulting signal really does behave like an echo, growing fainter and more distorted the more it's been disturbed along the way. Good scientific language often sounds more dramatic than the underlying reality turns out to be once you understand the mechanics, and that's a very different problem from a headline that invents drama. The actual research never claimed it all. As for where things stand right now, Google's quantum AI team continues expanding its research on multiple fronts, including work on neutral atom quantum computing systems announced in early 2026 alongside its ongoing superconducting qubit research on chips like Willow. The broader quantum computing field is actively working to build on the OTOC verification technique demonstrated here, exploring whether similar, verifiable quantum advantage results can be achieved across other genuinely useful scientific problems, rather than isolated, one-off benchmark tasks. Nobody serious in the field is claiming a fundamental law of physics has been broken, or that reality itself has been altered in any sense. What's actually been demonstrated is that a real quantum processor can perform a specific, scientifically meaningful, independently verifiable calculation dramatically faster than the best classical supercomputers currently available, using a technique borrowed conceptually from some of the strangest, most theoretical corners of modern physics. If you've stuck around this long, you already know this isn't the kind of story that needed an exaggerated headline to be worth your attention, and I'd rather tell it straight than dress it up further than the actual physics already supports. What's genuinely true here is stranger and more interesting than broke reality in the most useful sense a science story can be. A real working demonstration of quantum hardware, doing something a classical computer genuinely cannot do efficiently, verified independently, built on mathematical tools that physicists also use to think about some of the deepest open questions about black holes and the nature of information itself. If this kind of deep dive into real sourced science and technology news is what you come here for, subscribing helps a lot. Let me know in the comments whether you'd want to see this kind of quantum echo technique. Eventually applied to studying black hole physics directly, it genuinely shapes what we cover next, and sharing this with someone who'd get a kick out of it is the easiest way to support the channel.